All right, so we finished up derivatives. So we have the formula for the derivative. We've done a bunch of examples. They get involved, but that's you should expect that as we go on in the course. The higher level math you learn, the more involved it gets. Now let's talk about area. So we're going to talk about integration. So if we have the curve y is equal to, they're using capital F of x here. So if we have that, if we have a function that describes this, the area under the curve from x equals a to x equals b is given by area is equal to the integral a to b f of x dx. And so we're assuming, f of x is greater than or equal to 0 because we're talking about, the actual whole area under the curve. If we also have, so if that, trying to get my language correct here. If the curve C traced out by x is equal to little f of t, y is equal to little g of t, and alpha is less than or equal to t, less than or equal to beta, we can figure out what the integral is by this rule. So first thing I want to note is that if I compute the differential dx, this is going to be f prime of t dt. And I get that from up here. So what I have then is that the integral from a to b of y times dx, so this is, thinking of the function y. If I think about, this is a u substitution, I'm making the substitution x is equal to f of t, then I can say that this is then the integral from alpha to beta, y is equal to g of t, dx I've already computed, it's f prime of t dt. Okay, so let's do an example. So there's only one example for the integration. So find the area under one arch of the cycloid. So they like to go to the cycloid here. X is equal to r times theta minus sine theta. Y is equal to r times 1 minus cosine theta. Okay, so what you should remember from the cycloid is this thing traverses, under one arch. This starts at 0. This is at 2 pi times the radius. So one arch goes from 0 to 2 pi r. So then my area is going to be given by, the integral from, 0 to 2 pi r of y dx. And so what this is going to be, so you can see that, if I make the substitution x is equal to r times theta minus sine theta. So let's talk about the bounds in a second. So I'm going to plug in y. So this is going to be equal to the integral then r times 1 minus cosine theta. And then I multiply by dx d theta d theta in this case. So for the bounds, we need to figure out at what value of theta does x equal 0 and does x equal 2 pi r? So by inspection, so sometimes you'll be able to invert this. This is not one of those cases. You have to do it by inspection. When theta is equal to 0, you get x is equal to 0. And when theta is equal to 2 pi, you're going to get x is equal to 2 pi r. So that gives me the values of theta for this. You could also, you could solve, so this equation can be inverted, the equation for y, if you don't want to just eyeball it. So if you set that equal to 0, because at these 2 points, the y coordinate is 0, if you solve that equation for theta, you'll get theta is equal to 0 and theta is equal to 2 pi. But anyway, I've done it by inspection. So this integrals from 0 to 2 pi. So now I just plug in for all the things I have. This is the integral from 0 to 2 pi times r times 1 minus cosine theta. Dx d theta is up there, so it's going to be r times 1 minus cosine theta d theta. So this is the integral from 0 to 2 pi. I'm going to pull out a factor of r squared because there's 2 r's there. I'm going to get 1 minus cosine theta squared d theta. Let's expand that out. So I'm going to get 1 minus 2 cosine theta plus cosine squared theta. Okay, so we just keep going. So I'm going to have 1 minus 2 cosine theta. You'll remember that the way we handle these cosine squareds and sine squareds is I write this as 1/2 plus 1/2 cosine 2 theta d theta. So this turned into all this. So this cosine squared theta turned into all that. 1/2 plus 1/2 cosine 2 theta. Okay, so now we can integrate all this stuff. This is r squared times theta minus 2 sine theta, because I'm integrating, plus 1/2 theta plus 1/4 sine of 2 theta, evaluated from 0 to 2 pi. So it's r squared times 2 pi minus sine of 2 pi, so that's 0, plus 1/2 times 2 pi. I'm going to have 1/4 sine of 4 pi, which is again 0. I'm going to subtract off what I get when I plug in 0. So I'm going to get 0 minus sine of 0 is 0, plus 1/2 times 0 is 0, plus 1/4 sine of 0 is 0. So this is r squared times 2 pi plus pi. This is 3 pi r squared. And so, so that's essentially what it is. You have to, I think the hardest part of this, let's see. So don't forget, when you convert this thing, you have to plug it into this formula. So it's g of t f prime of t, where those g's and f's are given as the parametric equations. And then, you also have to change these bounds. And I did this one by inspection, but let me show you how you can get the bound. So getting the bounds of the integral from the y equation. So one thing you'll notice with the region I'm trying to integrate over is that the y value at these 2 points, now dots in blue, the y value there is 0. So if I plug in 0 into the y, if I plug in 0 for the y equation, I get 0 is equal to r times 1 minus cosine theta. And so what this equation gives me, if I divide by r and add over cosine theta, it's going to give me cosine theta is equal to 1. And the places this happens is, so I know it happens at, 0 and 2 pi. And I can, check those against, so I do have to check those against the x values. And I can see that, if I plug in 2 pi for the x values, it gives me the correct x coordinates. So again, this is a little harder. You'll get practice with it. It is one of the more difficult things. I don't have any more examples. I don't know when this homework's due. I do plan on doing, some problems, working out a couple problems from this section for you guys, putting them up. I know I didn't last week because you guys had your exams. But anyway, so I'm going to stop the video here and we're going to move on to arc length next.